Welcome to the Empirical and Molecular Formulas video. On your screen right now are two definitions taken from the textbook of what an empirical formula is and what a molecular formula is. So let's go ahead and go over them, but before I start talking about them, you can go ahead and pause the video and write these down, take a screenshot, whatever you need to do if you do not already have these in your notes. So let's go ahead and get started with this. An empirical formula by definition is a formula with the lowest whole number ratio of elements in a compound. The empirical formula of hydrogen peroxide is HO. And so in parentheses we included what hydrogen peroxide really is. It's H2O2. So you have two hydrogens and two oxygens that make up a hydrogen peroxide molecule. We want to go ahead and get the lowest whole number as it states right here in the definition. And so we would have to divide both of these subscripts by a 2 to get our result of HO that's here. Now keep in mind that when you go ahead and divide, when I say you have to divide both of them by 2, you need to divide always every single element in the compound by the same number. So in this case it would be 2. If you had H3O3, you would divide both of them by 3 and so on. For a molecular formula, the definition for this is a chemical formula of a molecular, also known as covalent compound, that shows the kinds and numbers of atoms present in a molecule of a compound. And so going back to hydrogen peroxide, the molecular formula for that really is the H2O2, because that tells you that you have to have 2 hydrogens for every 2 oxygens to make up a hydrogen peroxide compound. So let's go on and do an example problem or two of how we figure out to calculate a empirical formula and how to take the empirical formula and figure out the molecular formula given the information in the example problem. Alright, so here's our first example problem. It states a compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound? And so the first thing that we need to know is that we need to assume 100 grams. When we assume 100 grams, what we can really do is change a percent to the amount of grams. So you can see over here, the 25.9% can go straight to 25.9 grams, and it's all because we assumed 100 grams up here at the top. So think about it this way. 25.9% of 100 grams is 25.9 grams. And so if you can get through that thinking and that logic, it's really easy to see how that conversion would happen. We want to go ahead and do that for both nitrogen and oxygen, but let's go ahead and do our work that's on the right-hand side of your screen, or the lower right-hand side on the right, for nitrogen, and then we'll go back to the oxygen. So what we want to go ahead and do is, once we figure out our 25.9 grams, we want to divide that by the molar mass of 1 nitrogen, so we can figure out how many moles of nitrogen we have from what our example problem is. And so from the periodic table, 14.01 grams is the molar mass of 1 nitrogen. I went ahead and divided these two numbers and was able to get 1.85 moles of nitrogen. So let's go ahead and do the same work for our oxygen percentage. So now on your screen you can see the 74.1% converted to grams, which is 74.1 grams. We divided over to the lower right hand side the 74.1 grams by 16 grams, which is our molar mass of oxygen, 1 oxygen that is. And we got this number of 4.63 moles of oxygen. Now the 1.85 and the 4.63 really aren't great numbers to work with, as we need whole numbers for any compound for the subscripts. In order to get these numbers to whole numbers, we want to go ahead and divide both of them by the lowest amount that we have calculated. And so on the side we have 1.85 being the lowest, but if we say we have 5 different numbers here, again you just want to pick the lowest out of all of them. We're then going to take every single mole amount that we have and divide it by that number to try to start getting some whole numbers here. So at the bottom left, that's what we just went ahead and started doing. So 1.85 divided by 1.85 is 1. Ignore the pink for right now. We'll talk that through in just a moment. Then next to that, you have 4.63 divided by 1.85, and that number comes to be 2.5. 1 and 2.5 still are not whole numbers, but they're going to be easier to work with than what our original mole amounts were. And so you can see now in the pink, we're going to start talking about that. If we multiply 2.5 by 2, we're going to end up getting a whole number of 5, and that's why we picked the 2 that's in pink. Now if you had 2.25, 0.25 is 1/4 of a whole number, and so we would multiply by 4. So whatever your decimal is, you might have to figure out what to multiply by. And notice I went into thinking about how fractions would work there, and that could be helpful. And so you want to multiply at this point by whatever number is going to get you whole numbers at this point. Once you multiply the 1 by 2, that's our nitrogen number, and so that's how we have N2 over to the right-hand side here. And 2.5 times 2 is 5, and that's our oxygen number. So our empirical formula is N2O5. Here's the other example that we'll go through really quickly. This is where we're going to tie in empirical formulas with molecular formulas. So let's go over the problem really quick. Calculate the molecular formula of a compound whose molar mass is 60.0 grams per mole, and the empirical formula is CH4N. So the first thing we need to go ahead and do is figure out the molar mass of our empirical formula. Again, not going into detail, I went ahead and show all my work here so you can at least go through. The first column is the amount of each element multiplied by the mass that's from the periodic table, and you add them all together to get the 30.06 grams per mole. And so you always, in step 1 here, want to get the molar mass of your empirical formula. The next thing you're going to want to do is now we're going to take into account this molar mass and the molar mass that's given into the problem. So for step number 2, we want to take the molecular molar mass and divide it by your empirical molar mass to get a whole number that we can use. So if we go ahead and plug in our numbers, we should get roughly 2. It's very close to the number 2, which means all we have to do is take our empirical formula, the subscripts that we see there, and multiply every one of them by 2. So you can see at the bottom of your screen that's what we did, and so now our molecular formula is C2H8N2. Before we go ahead and end this video, I just want to bring to your attention that you really can combine both example problems we just went over. So instead of this example problem that we just started with, example 2, giving us an empirical formula from the get-go, it could ask you to solve for the empirical formula and then go into figuring out what the molecular formula is. So go ahead and practice these problems, and you should have all the information needed to do any kind of empirical formula or molecular formula problem that's thrown your way.